our next speaker, Maria Urinova, and this is an invited, contributed talk, so she's also one of the recipients of the Travel Award. So let's welcome Maria.
This is because of Hi, my name is Maria Urinova. I'm a PhD student at the University of Edinburgh, but this work has been done as part of an internship at Google, where I work with Dave Moore and Matt Hoffman. And today I'm going to talk about how we can use probabilistic programming in order to automatically parameterize our models. So what is the problem we try to solve? Well, basically, the performance of our inference algorithms really depends on the shape of the posterior of interest. These are two standard examples. So on the left, we see X and Y that are highly correlated. And if we use something like Metropolis Hastings or thank you for doing this poster. If we use something like Metropolis Hastings or give something to explore this distribution, it's going to be very inefficient because we have to make very small steps in order to explore this. If we use something like HMC, that might help because we make use of the gradient of the distribution, but HMC also has its pathological cases where it doesn't work well. For example, this is News Funnel, in which X and Y have very strong nonlinear dependence, and the shape of their joint distribution is of a funnel, which is kind of has very low curvature on the top over there, but it's very curved inside here. So if we try to explore this with HMC, what will normally happen is that we'll explore this bit pretty well, but we won't be able to go inside of this funnel. So instead of sampling directly from News Funnel, we could have instead sampled two independent standard Gaussian variables, X tilde and Y tilde, and then scale them appropriately so that we recover the original distribution. And this, of course, will mean that it's a much easier inference problem to explore this distribution over there because we know how to sample from a Gaussian distribution, right? This is easy. And this is exactly what model reparameterization is. We want to express our express our model in terms of different parameters and define a way to recover our original parameters in order to improve inference. And in this case, the original specification that we had is this is the centered parameterization for News Funnel, and the one where we sample from standard normal is the non-centered parameterization. Of course, in this case, it's very easy to see that it's better to use a non-centered parameterization because we don't have any data. So we know how our distribution looks like. And of course, we want it to look like a standard normal, right? It's easy. But if we have data, things might become more complicated. So let's explore this with a small example. Here, this is a very simple hierarchical model where theta is a standard normal, mu has mean theta, and y is some data vector where each data point has mean mu. This is, again, the centered and the non-centered parameterizations for this model. In the non-centered case, we only parameterize mu, as theta is already a standard normal. Because this is a very simple example, we can analytically derive the posterior in this case, so the posterior of theta and mu given y, or the posterior of theta of epsilon in the non-centered case. And so we do that, and what you see here is the posterior plotted in both the centered and the non-centered case different values of Q, where Q is the ratio between the number of data points, so how much data we have, and the standard deviation of this data. And you can see that the shape of the posterior changes significantly based on the data we observe. So if Q is small, so if we have just a little bit of data, it's sort of intuitive that our posterior will sort of look like the prior, so we want to use no-centered parameterization because that's just a standard normal. And then as Q grows, we see that in the no-centered case, the posterior becomes quite ill-conditioned. So what is our goal here? Basically, reparameterization is important. So we want to parameterize our models the right way, but it's not so trivial to do so because it depends not only on the model we have, but also on the data we observe. In probabilistic programming, in particular, the dream is that you just specify a model and then inference will happen magically and you won't have to think about any of this. But this is not the case. Even when we have black box inference algorithms, we need to think about things like reparameterizing the model in order to avoid some pathological cases like New's funnel, for example. So our goal is to free modelers of the need to have to choose a model parameterization and to help them do this automatically. And for this, we'll first need a way to do this with probabilistic programming. So in our case, we used Edward 2, but it's important to know that other probabilistic programming systems either already have a way to reparameterize if the user wants to, or they really should. In Edward, we have, so a model in Edward is just a function that defines some random variables, which are some Edward 2 objects, and they return data. In the centered and non-centered case, there's a very small difference. It's just that instead of declaring the variables, directly, we firstly declare them we declare standard normal random variables and then shift and scale. And so how can basically what we want here is to move from the centered version from the left to the right automatically, or on user's request, rather than having to write this model over here explicitly. And in Edward 2, that's done with a mechanism called interceptors. So what is an interceptor? This is just a function that says how you want your random variables to be constructed. So this is, if you look at the NCP function over there, this is just a function that takes a random variable constructor and takes the arguments to this constructor, and then says, instead of constructing this random variable, which will be random variable constructor called on these keyword arguments, we construct a random variable with mean 0 and standard deviation 1, and then we scale and shift with the appropriate keyword arguments. And if we write any code in the context of this interceptor, what happens is that each of these calls to each of the constructors of random variables are actually not called directly, but this function is called. So whatever it says is executed. And this is how one can reparameterize the model in Edward 2. And now that we have this, now that we can do this with a simple command, we can try to find a way to automatically reparameterize our models. And we came up with two strategies. One is, the first one is called interleaved HMC. This one doesn't really choose a reparameterization, but tries to combine the two. So it tries to combine centered and non-centered parameterization. The way it does it is that you just take one, so for every sample that you want to make, you make two samples, one in centered space and one in non-centered space. And this has been done before for KIP sampling by UMN 2011. But in our case, our contribution is that this is done entirely automatically. So the user doesn't have to specify both a centered version of the model or target distribution and a non-centered one, and then a function that transforms the samples from centered to non-centered or vice versa. But they only specify one model, the centered model, and everything else is done automatically. The second strategy we developed is called variation inferred parameterization. And here while with interleaved HMC, we combined centered and non-centered parameterization to sort of take the best for both worlds, but not really have to decide on which parameterization is better. Here we are trying to find good parameterization. We try to use a concrete thing. And why is this hard? Well, if we have, say, n parameters in our model, the possible parameterizations for this model will be 2 to the n, because for each parameter we have to choose, and we're going to use its non-centered or centered version. And so what we want to do naturally is to use variable-based methods to explore this exponential space and sort of find a point in it which is a good parameterization. So the first thing we have to do is to find a continuous parameterization of the non-centered parameterization that sort of allows us to interpolate between centered and non-centered. And this is what we have here. So for a variable set that has a mean mu and standard deviation sigma, instead of doing the non-centered reparameterization where we will sample from a standard normal, we sample z tilde, the reparameterized variable, from a distribution with mean a times mu and standard deviation sigma to the b, and a and b are some values that are not part of our model. So if you look at this more closely, you will see that when a and b are 0, that means the non-centered parameterization. That would be equivalent to the non-centered parameterization. And when a and b are 1, that would be equivalent to the centered parameterization. So now what we want is to somehow explore this space, this continuous space, and find values for a and b that are going to be suitable for our problem. And the way we did this is that we rely on the conjecture that if a mean field, if we can approximate our distribution well with mean field variational inference, that means that it will also be suitable for sampling with HMC. So, in other words, if our distribution looks like an independent Gaussian, then that's good, and that's what we're aiming for. And so what we did is that we reparameterize our model this way, and we collect what we call parameterization parameters, which are a and b in this case, and we also create a variational family, mean field variational family, and then we optimize an elbow so that we simultaneously are trying to fit a mean field Gaussian to our distribution, and also we are changing the shape of this distribution by controlling these parameterization parameters. And here you can see an illustration. So on the top row, you see the white lines are the mean field Gaussian that we are fitting on this distribution, and the actual distribution is the reparameterized Niel's funnel for different values of a and b. And you can see how this, if we are not thinking of this as changing the shape of our distribution, but if we're thinking of it as just having Niel's funnel and working with that, you can see what's actually the actual effect on the variational family we're using if we look at a and b as variational parameters. All right, and so we have some preliminary results which confirm our speculation that interleaved HMC will be robust compared to fully centered or fully non-centered parameterization, which we were expecting because it sort of combines both of them. So if one of them is good, then it should make at least that much progress too. It should be at least as good. And then we also have some preliminary results suggesting that VIP, so this variational inferred parameterization, if we combine it with HFC, so we use variational inference to find some good parameterization, and then we combine it with HFC afterwards to actually do sampling. This finds reasonable parameterization based on the effective sample size we got. And one very interesting thing we found is that sometimes, in some cases, mixed parameterizations that VIP finds might be potentially superior to a fully non-centered or fully centered model. And we are very excited to look into this further. And I think I'll finish with that. Thank you very much. Any questions?